Hello everyone, I'm Gaetano Cacciamilio from the University of Waterloo. I'm recording this virtual presentation because unfortunately my co-authors and I are unable to attend Spaa in person this year. Today I'm going to present our work Persistent Hybrid TM via Fastpath Fine-Grained Locking. This is work that I did with my supervisor Trevor Brown at the University of Waterloo, along with our colleagues Ruat and Ravi from the University of Southern California. I'll begin by discussing the problem. In this work, we're interested in concurrent data structures because they're useful in a variety of different applications. For example, we might have a set implemented as a search tree, which can serve as an in-memory database index. Our concurrent data structures are going to be accessible by many threads, but with this comes various problems, including issues related to synchronization or cache utilization. We want our concurrent data structures to have high performance. Not only do we want high performance, but now that we have access to non-volatile memory, we also want persistence, meaning after a power failure, we want to be able to recover a consistent state of our data structure. And of course, achieving these things is non-trivial. Before I continue, I'll just quickly review the setting that I'm discussing here. This is the traditional memory hierarchy, showing how every RAM fits into this hierarchy. Traditionally, we have CPU registers, cache, and DRAM as volatile storage, and now we have NVRAM along with SSDs and hard drives as persistent storage. Because of the fact that the cache is volatile, if we want to ensure that data in the cache is persisted, we have to explicitly flush it from the cache back to main memory, and then we need to fence in order to wait for those flushes to complete. A caveat to this is that some new processors have EADR, or Extended Asynchronous DRAM Refresh, which effectively gives them persistent caches. This is not going to be very relevant during this talk. I'll just note that for our algorithms and our contributions, they confer the same benefits on systems both with and without EADR. All right, so when you're designing concurrent data structures, how can you achieve easier synchronization? Well, you can use a mechanism known as transactional memory, or TM. With a TM, you can mark blocks of code as transactions, and you can execute multiple transactions concurrently where the synchronization is handled for you via the TM. The TM itself can be implemented in software, or if your processor supports it, it can be implemented in hardware. If you combine the use of both, we refer to this as a hybrid TM or a HyTM. A persistent TM not only handles synchronization for you, but it also ensures that the effects of committed transactions will be written back to non-volatile memory. There are various examples of prior persistent TMs, including Nemoscythe, DoTM, Pisces, and various others, and these are examples of software-only persistent TMs. For hybrid TMs, we have examples such as hardware transactions in non-volatile memory, PhyTM, or DHTM, but these are examples of persistent hybrid TMs that do not work on current hardware because they're based on proposals or changes to hardware that does not actually exist. And we have some other examples such as Crafty and SPHT, which are persistent hybrid TMs that do work on current hardware. Unfortunately, the persistent hybrid TMs that work on current hardware are lacking. For example, the existing state-of-the-art SPHT has some important performance problems. It has a trivial global lock fallback path. It does not allow concurrency between hardware and software transactions. It does allow disjoint transactions to block one another, and it has no memory reclamation in its public implementation. And in this work, we're seeking to provide a better alternative for persistent hybrid TMs with an explicit goal of designing and implementing a practical persistent hybrid TM with a non-trivial software path and one that allows concurrency between hardware and software transactions. And this leads to our contribution. So in this work, we've designed a new approach to persisting hardware path transactions, and we use this new approach to design and implement a new persistent hybrid TM that we call Nv-Halt, or non-volatile hardware-assisted locking transactions. In Nv-Halt, our hardware transactions are primarily used to acquire fine-grained locks. Now, if you're familiar with TM, this might seem counterintuitive, but I will show you that this is very effective. We provide different implementations of Nv-Halt, each with a different progress guarantee, and we also introduce a new notion of progress tailored specifically for hybrid TMs. Before I can get into the details, I'll need to cover some background, so starting off with some background on transactions. So the interface to a TM, we can begin a transaction, commit a transaction, or voluntarily abort a transaction. A TM will typically track a read set and a write set, meaning the set of all addresses that are read by our transaction and the set of all addresses that are written to by a transaction. If the write set of one transaction overlaps the read or write set of another transaction, we refer to this as a conflict, and conflicts will cause aborts. For hardware transactions, we're interested in the Intel RTM implementation, where we begin with xbegin, commit with xend, or abort with xabort. In this case, the read and write set are tracked for you by the hardware via the cache coherence protocol. One major issue with hardware TM is that it allows for spurious aborts, meaning a hardware transaction can abort for any reason whatsoever. This means that hardware TM offers you no progress without a software-based fallback path. Now, one thing that can cause spurious aborts is flush instructions. If you attempt to flush inside of a hardware transaction, it will cause an abort, which of course complicates the design of persistent hybrid TMs. A bit more background for correctness and progress in TM. The default correctness condition in TM is opacity, which says that if we have a set of all transactions, including aborted ones, it must be equivalent to a sequential execution where every read returns the value of the latest committed write. For progress, we have weak progress, which says that if we have some transactions that are aborting, then there must exist a concurrent conflicting transaction. And this means that if we have n conflicting transactions, then possibly all n of them are aborted. This is in contrast to strong progress, which says that if we have n conflicting transactions, then at least one must commit. This leads naturally to one of our contributions, the introduction of a new progress condition that we refer to as C abortable progress. So as I mentioned, a hybrid TM cannot guarantee progress without a software-based fallback path. This means that if we include the fast path in our correctness arguments, then we will never be able to achieve strong progress, because even if we have only one hardware transaction, then this transaction can still spuriously abort. So we want a progress definition that will exclude the fast path. One observation here is that typically when we implement hybrid TMs, we often use an optimistic fast path where we bound the number of times that we can abort before falling back to a software-based path. And we capture this with our notion of C abortable progress. We say that a TM is C abortable progressive if it is allowed to abort for any reason at most C times, after which it must follow weak or strong progress. And if C is a constant, then we say that the TM is O1 abortable progressive. All right, so now we can talk about our new persistent hybrid TM, Nv-Halt. Nv-Halt is a two-path persistent hybrid TM with a hardware fast path and a software fallback path. It guarantees opacity, and it is O1 abortable progressive. We have both an O1 abortable weak progressive implementation and an O1 abortable strong progressive implementation, and we'll talk about both. Our hardware transactions are primarily used to acquire fine-grained logs. And our persistent mechanism here is a logging-based approach that is inspired by the state-of-the-art persistent software TM. All right, well, let's start out by talking about the data structures that Nv-Halt relies on. So for our software path, we use a read set and a write set, which are implemented as dynamically sized tables. And for our strong progressive implementation only, we also have a global clock. On the hardware path, we use per thread logs. These are fixed size. All of the addresses in Nv-Halt are protected by version locks, and these version locks are stored in a lock table. For our weak progressive implementation, each one of these version locks, along with its version number, has a general lock bit, which is set whenever a software transaction or a hardware transaction claims the lock. And in the strong progressive implementation, we have that same general lock bit, which is set by either software or hardware transactions. And we also have a hardware lock bit, which is only set by hardware transactions that claim the lock. All right, so let's start out by looking at the software path for Nv-Halt for the strong progressive implementation. So when you begin a transaction in this case, you're going to read the global clock and you're going to record a local copy of that clock that you observed at the start of your transaction. We'll come back to this later. So now suppose we want to perform a store on the address of A. We're going to check if A is locked. If it is locked, we're going to abort. If it's not locked, then we're going to add A to the write set. Similarly, if we want to load A, we check if A is locked. If it's locked, we abort. If it's not locked, then we add it to the read set. Straightforward. So what do we do when we want to try to commit? Well, the first thing is we check if we're a read-only transaction. If it is, then we're done. We don't need to do anything else. If it's not a read-only transaction, then we're going to sort our write set. We do this to avoid issues that can arise by two transactions accessing the same addresses, but in a different order. After sorting, we're going to try to acquire our write set locks. If we fail to acquire any of these locks, then we need to abort. But if we acquire all these write set locks, then we're going to attempt a compare and swap operation to increment the global clock to 1 greater than the value that we observed at the start of our transaction. And if we fail this compare and swap operation, then that means that there must have been a concurrent software path transaction that committed during our transaction. So in this case, we need to perform read set validation to check for conflicts between that software path transaction or other software path transactions, as well as possibly concurrent hardware path transactions. However, if we successfully perform that increment to the global clock, then that means there were no concurrent software path transactions that committed during our transaction. So in this case, we only need to validate the read set to check for conflicts that are with concurrent hardware transactions. And we can differentiate between conflicts of hardware and software transactions because of that hardware only lock bit in our version locks. Now, in either case, if we fail to validate the read set, we must abort. If we successfully validate the read set, then we go forward with performing and persisting the writes. And importantly, this is happening while we still hold the locks. So once we finish performing and persisting the writes, then we can release the locks, and now we're done. All right. So in this case, the strong progressive implementation is giving us a way to bypass validating for concurrent software path transactions under some conditions. And in this case, the conditions are when we are successful in performing that increment of the global clock. All right, so let's look at our hardware path. In this case, when you begin a transaction, it's equivalent to performing the xbegin operation because we're using Intel RTM. If we want to perform a store of A, then we're going to read A's lock to check if it's locked. If it is locked, we're going to abort. If it's not locked, then we're going to lock A and we're going to log this write in our private per thread log. And of course, this lock is going to set the hardware lock bit along with that general lock bit. And in this case, we're going to immediately perform the write because we're in hardware. If we want to do a load of A, then we just need to check if A is locked, reading its lock. If it is locked, then we abort. And if it's not locked, we don't need to do anything else. Now, in this case, we're using encounter time locking, which is different from our software path, which is using commit time locking. We could, if we wanted to, lock somewhere near the end of our hardware transaction, but this would mean that we would need to access or store additional metadata, and we would need to do some additional work in hardware, and all this would likely lead to more aborts, which we would prefer to avoid. All right, so how do we commit on the hardware path? Well, trying to commit in hardware is equivalent to calling xend. If we successfully return from xend, then our hardware transaction has committed, meaning all of those writes will have taken effect and will be visible to other threads. Once we return from xend, we're going to check if our write log is empty, essentially saying, are we a read-only transaction? If it's empty, then we're done. If it's not empty, then we need to move forward with persisting the writes. Now, importantly, we have already performed the writes in hardware, and we still hold the locks. We claimed the locks in hardware, and we still hold the locks, so we can go forward with persisting, after which we will release the locks, and then we're done. Great. All right, so now let's take a look at how we can transform our strong progressive implementation into our weak progressive implementation. We're looking at the commit path of the software path here. Now, in this case, we don't have to sort the write set anymore because we don't care about the problems that might arise by the different order of accesses, so we're going to skip over that step, no more sorting. And we also don't have a global clock anymore. So not only do we not need to read at the start of our transaction the global clock, we cannot do anything here with the global clock, and we don't have any hardware lock bit. So once we acquire our write set locks, we're going to go straight into normal read set validation, which is going to check for conflicts for concurrent software or hardware path transactions. And then the rest is the same. For our hardware path, the only difference is when we lock during a store, there's no longer a hardware lock bit, there's only that general lock bit. Great. Now, there are some situational optimizations that we can do in Nv-Halt. In particular, instead of using a lock table, if we're allowed to change the layout of user data, we can get some performance benefit by inlining locks with user data in certain workloads. And that would look as it's shown below. In a lock table, we would have a mapping between the address of user data and the lock. And when we inline the locks, we interleave user data in the locks. Now, you might ask, why do we want to lock in hardware at all? Well, I'll first note that there's an existing result from my co-authors which says that in an opaque, volatile hybrid TM, you have to read shared metadata on the hardware path. But what about in the persistent setting? Can we have a persistent hybrid TM that does not write to shared metadata in the hardware path? Let's take a look at an example. So in this case, we have two transactions, T1 and T2, and they're going to access three variables, A, B, and C. Let's assume that they're all initially 0. T1 is going to attempt to write A equals 1 and B equals 1, and then T2 is going to perform if B equals 1, then set C equal to 1. And they're both going to execute in hardware. So let's first have T2 sleep, and then T1 is going to progress. It's going to observe A and B are unlocked, excuse me, and then it's going to move forward with performing its writes, and it's going to set A equal to 1, B equal to 1, and it's also going to log these writes. We're going to assume an approach similar to Nv-Halt because we're in a persistent hybrid TM. Now here, there's no locking, and this write to the log is not a shared write. The logs are private, so that's important. Now we're going to commit our hardware transaction, and we're going to start persisting our log by initially persisting A equals 1. Now, an important thing to note here is if we only persist some of the transaction's writes, then when we recover, we're going to ignore that all of the writes that were partially persisted. Maybe you see where I'm going with this. So now we're going to have T1 sleep. Now, T2 is going to wake up, it's going to observe B and C are unlocked, and it's going to also observe that B equals 1, so it's going to move forward with writing C equals 1 and logging C equals 1. It's going to commit its hardware transaction, it's going to persist the write of C, and then it's going to commit. And now we're going to have our system crash. So now what will we recover? Well, we're going to recover A equals 0, B equals 0, and C equals 1. Hopefully it's obvious why we recover C equals 1. We fully persisted T2. Hopefully it's also obvious why we recover B equals 0. We never persisted any writes of B. And we recover A equals 0 in this case because we only partially persisted T1, so we're going to ignore any of its updates. We're effectively reverting it in this case. And this resulting state is inconsistent. It violates opacity. So the conclusion here is that the hardware transactions have to write to shared metadata in the persistent setting. And this is a big inspiration for our approach to Nv-Halt, where we are locking on the hardware path. All right, so let's see how effective this is. So this is a comparison of performance versus the existing state of the art. This is for an A-B tree with a maximum of 1 million keys, where we're using a uniform key access pattern. This is at a 90% read-only workload. Y-axis is operations per second. X-axis is number of threads. The gray bar here is the state-of-the-art persistent software TM trinity. The yellow bar is the previous state-of-the-art persistent hybrid TM SPHD, and then all three of the other bars are implementations of Nv-Halt. So the red bar is the strong progressive implementation of Nv-Halt. The purple bar is the weak progressive implementation of Nv-Halt, where we're using a lock table. The strong progressive is also using a lock table. And then the blue bar is the weak progressive implementation with our situational optimization of inlining the locks. Now, one of the immediate things that you can take away from this is that all three of our implementations are already achieving a significant throughput improvement to the existing state of the art. Another takeaway here is that between our strong progressive and weak progressive implementations, generally speaking, the weak progressive implementation performs better, which is not surprising. And we can also see that when we are able to use our situational optimization in line in locks, then we can sometimes get a large performance benefit as well for certain workloads. Now, an important thing to note here as well is that SPHD does not do any freeing, as I mentioned, whereas Nv-Halt has a non-trivial memory reclamation cost. So we're getting better throughput compared to SPHD despite that fact. Now, we also wanted to understand the implications of various overheads of persistent hybrid TMs. So we performed an ablation study comparing Nv-Halt against SPHD. So in this case, the blue bar without any hatching is our weak progressive implementation of Nv-Halt with our inline locks optimization. And then each bar after that is going to remove some overhead related to the persistent hybrid TM. So the crosshatch bar is going to remove the overhead of writebacks by replacing flushes and fences with no ops. The star hatch bar is going to further replace an overhead by replacing all uses of non-volatile memory with DRAM. So in this case, we essentially get free NVRAM because we're faking it, right? And then the last bar that is hatched with circles is doing all the previous removals of overhead, along with removing the overhead of persisting hardware path transactions by removing any synchronization for persisting those transactions. And it's the same breakdown in this case for SPHG, the yellow bar. So the non-hatched bar is the regular implementation, and then each successive bar is removing some overhead. Now, an important thing to note here is that there's not a big difference for Nv-Halt between our actual implementation and any of the revised implementations that remove some overhead. And the reason for this is that our approach to persisting hardware path transactions and our synchronization is already quite efficient. We are allowing for concurrency between software and hardware path transactions. Unlike SPHT, where there's a large difference between its base implementation and the implementations where it's removing some of these overheads, in particular, the synchronization for persisting hardware transactions. SPHT pays a massive cost for persisting its hardware transactions. With the approach taken by SPHT, you could not have a non-trivial software path. You could not have concurrency between software and hardware transactions, and that is displayed here. Now, another thing to note here is that because of the fact that there's not much of a difference between the different overhead implementations of Nv-Halt and its base implementation, if NVRAM were to improve in terms of better latency and bandwidth, we would be able to reap those performance improvements without having to make algorithmic changes, whereas SPHT might need to make some changes if they want to improve based on that hardware. All right. And one other experiment that we did, which is interesting, is a comparison of energy consumption. In this case, the y-axis is average joules per commit or average energy per commit. It's the same A/B tree, but now we're looking at a 50% read-only workload, so there's more updates in this case. We're looking at Nv-Halt, the weak progressive implementation, along with Trinity and SPHT for their base implementations, along with the implementation where we remove the overhead of writebacks. Now, in this case, we can see that Nv-Halt consumes significantly less energy per commit in all thread counts, but we're mostly interested in the 96 thread count because this is the maximum number of threads in our system. And when you measure energy consumption with perf, you can't differentiate between different cores. All right. So with that, I'll conclude. I'll just note that there are many other details in the paper, including some additional experiments that you might be interested in. If you have some questions or you want to contact me, please feel free to email me. My email is in the paper, or you can find it on the Multicore Lab website for the University of Waterloo. Thank you.